Hi all, today we discuss rank nullity theorem, theorem 2. We have already discussed this theorem in your degree course, but there is a repetition of that theorem. The statement is that V and B, WB vector space is over the field F, and let T be a linear transformation from V onto V into W. Suppose that V is a finite dimensional vector space. Okay, so that means this theorem works only on the case of finite dimensional vector space. V is finite dimensional, whatever be this W. Then you can get this identity rank T plus nullity T is equal to dimension of V. This rank T is the dimension of the range of T, and nullity T is the dimension of null space of T. We have already discussed this in the last lectures. Now we will prove that by taking a basis of n, say alpha 1, alpha 2, alpha k. So the dimension of null space is k. We will prove that n minus k is the dimension of the range of this linear transformation T, and that range is a subspace of this W. Okay, even though the W is infinite dimensional, this will work. The only thing is V should be finite dimensional. Since this alpha 1, alpha 2, alpha k are the basis for this null space, say n, we can say that this T of alpha 1 equal to T of alpha 2 is equal to etc. equal to T of alpha k is 0, because these are all elements of the null space. Null space contains the vectors whose image is 0. So this is the case for alpha 1, alpha 2, alpha k. And if you consider this alpha 1, alpha 2, etc., alpha k a basis of null space, you can say that this is linearly independent and spans this null space, spans n. Okay, so using this linearly independent, you can consider this a linearly independent subset of V, but we know that every linearly independent subset of V can be extended to a basis of V. So I'll extend this linearly independent set to a basis of V, say alpha k plus 1, etc., alpha n. Okay, and our assumption is dimension of V is n. Okay, we extend this linearly independent set to a basis of V. So we will prove that this set is the collection of the remaining elements alpha k plus 1, comma etc. alpha n. This contains exactly n minus k elements. So this is the basis for this is our claim. We will prove this basis for range of T. Okay, and the range of T is defined as the dimension of the range of T is defined as the rank of T. Then rank of T can be written as n minus k. Then consequently we can get k plus n minus k is equal to n. So once you prove this is the basis for range, we are done. So in order to prove this is the basis, we first write every element of the range can be expressed as a linear combination of this. So if we choose an element from the range, say beta belongs to range of T, we can write this beta as some T alpha, beta is equal to T alpha for some alpha belongs to V. Okay, so that means beta, since beta is an image, then that is an image of some element of V, say alpha, but V has the basis alpha 1, alpha 2, etc., alpha n. So this alpha can be written as C1 times alpha 1 plus etc. Ck times alpha k plus Ck plus 1 times alpha k plus 1 plus etc. plus Cn times alpha. Okay, now find T alpha. T alpha can be written as T of this, that is C1 times T alpha 1 plus etc. Ck times T alpha k plus etc. And the next will be Ck plus 1 times alpha T of alpha k plus 1 plus etc. Cn T alpha n. Okay, this is the form of T alpha, but T alpha is beta and beta can be written as this T alpha 1 is 0 because alpha 1 is an element of the null space. So up to this term you can get 0 because these are the elements of null space. Then the remaining will be ck plus 1 t alpha k plus 1 plus etc. t ck cn t alpha. Okay, this shows that the vectors t alpha k plus 1 etc. t alpha n spans range of t. Okay, now we will prove that this is linearly independent. These vectors t alpha k plus 1 etc. t alpha n as linearly independent. To prove this is linearly independent, we consider the linear combination sigma I is equal to k plus 1 to n ci t alpha equal to 0, and consequently we will prove that the ci's are 0. So first you assume the linear combination of this, say ci plus 1 t alpha k plus 1 plus etc. cn t alpha n equal to 0. Then if this is 0, we can say that t of ci plus 1 alpha I plus 1, this is our alpha I plus 1, sorry, this is k plus 1 and this is also k plus 1, ck plus 1 alpha k plus 1 plus etc. cn alpha n equal to 0. Since this t is the linear map, so you can consider this expression as t of this. Okay, what do you mean by this? T of something is equal to 0. This shows that this is an element of the corresponding null space of t. Okay, because the image of this vector is 0. So if this is 0, this is an element of a null space of t, then this can be expressed as a linear combination of elements of the base elements of n. Then this is ck plus 1 alpha k plus 1 plus etc. plus cn alpha n equal to linear combination of the basis vectors of null space. So that is alpha 1 alpha etc. So I'll write it as in the textbook they are considering xk plus 1 etc. This is our xk plus 1. I'll write it as xn t alpha n plus, sorry, that is, here we have cn. Here I write that is c1 alpha 1 plus etc. I use this ci's instead of xn. So ck alpha k. So this shows that when you transpose to one side, you can get this expression as c1 minus c1 alpha 1 minus c2 alpha 2 minus etc. minus ck alpha k plus ck plus 1 alpha k plus 1 plus etc. cn alpha n equal to 0. So this expression is 0, but we know that alpha 1, alpha 2, alpha n are basis elements of V. So whenever this combination is 0, we can get C1 equal to C2 equal to etc. equal to C n equal to 0. In particular, this Ck plus 1, Ck plus 2 etc. Cn is equal to 0. This shows that this this vector, this t alpha 1, t alpha 2 etc. t alpha n, this set is linearly independent as well. So this spans S and this spans range of t, and these are linearly independent. So this form a basis for range of t. Therefore, the dimension of range of t is the number of elements of this. Okay, we have assumed that the dimension of null space as k and dimension of the range, that is rank t, we have proved that is n minus k. Consequently, this sum is n, okay, which is equal to dimension of e. So this proves rank nullity theorem. Now we have the last theorem of this section, theorem 3. If A is an m by n matrix with entries in the field f, then row rank is same as column rank of a matrix. If you consider an m by n matrix, then row rank is same as column rank. The row rank is defined as the dimension of the row space. Similarly, the column rank is the dimension of column space. Okay, both are entirely different elements of or subspace of vector space. If you consider A is a matrix of order m by n, then row space row space is always a subset of f n by 1. This is f cross, I'll write it as f cross etc. cross f n copies. Okay, and we consider column space. Column space is a subset of, you can consider this as f m by 1, or you can consider this as f n by 1 by n. Okay, so row space is a subspace of some vector space, and this is the entirely different subspace of entirely different vector space f m by 1. Now you consider this A is equal to a11 etc. a1n, am1 etc. amn. This is the matrix A. Then what we have written here is a11 etc. a1n, that is one row, that is an element of one row n column vector. Okay. Similarly, each row is each row have the same parity, and in the case of column space we have this one. So that is a matrix of order m by 1. So each of these columns is an element of this f m by n. Now we will prove that consider these two subspaces, and the dimension should be the same. So that is what we call row rank and column rank. For that we consider a linear transformation T x equal to lambda x corresponding to this A, that is defined as T x1 x2 etc. xn equal to A times x1 etc. xn. So this multiplication is defined because this is m by n and this is n by 1, and consequently this is an element of f m by 1. Okay, and this is an element of f n by 1. So each n by 1 column matrix is transformed to m by 1 column matrix. Okay, so this is the action of this T to this column vector. Okay, now we consider then what is the relation between this matrix and T. That is the first thing. When you consider the null space of T is the solution space for the system x equal to 0, because null space of T is defined as set of all x. If we write this is capital X, this is our capital X, then set of all x such that Tx equal to 0, that is set of all x such that Ax equal to 0. So this is the NT is the solution space of this T. Now that is what we have written here. The set of all the null space of T is the solution space for the system Ax equal to 0, that is the set of all column matrix x such that Ax equal to 0. The range of T, in the other way, the range of T is the set of all m by n column matrix y such that Ax equal to y. So when you consider the range Rt, then that is set of all y such that y is equal to some Tx, that is set of all y such that y is equal to Ax. So this is the range, but we know that so this can be written, range can be written as set of all x, okay, such that x belongs to this f m n by 1. So this is the range, this is Ax. So we need to find the dimension of this range. So we will write it as each Ax can be written as x1 a1 is the first column, a11 a21 etc. am1 plus etc. xn, this is an1 etc. this is a1n etc. amn. So you can when you consider the product of this a into x, this is x, x1, x2 etc. So here we have x1, x2 etc. xn. Then the first term will be a11 x1 plus a12 x2 plus etc. So when you expand this, you will get the same thing. The first term of this will be a11 x1 plus etc. The last term will be a1n xn and so on. So this sum will give the first entry of this ax and the second entry of ax and so on. So we can say that this ax equal to ax can be considered as the each ax or range of t. If you choose any element of range of t, that is a linear combination of columns of A. Okay, so this shows that the column space or range can be range of t can be spanned by range of t. That is what we written here, RT. This can be written as span of or range of t can be spanned by columns of A, say A1, A2, etc. A. So this represents the columns of A. Okay. So when you consider linearly independent columns from this, you can get the basis vector for range of t. Okay, because this spans range of t, then collect all linearly independent vectors from this. So this shows that column rank of A is same as column rank of A means number of linearly independent columns in this collection. So that is same as the dimension of range of t. So that is nothing but column rank of t. So from this you can write this is column rank of A is same as rank of t. Okay, rank of t. Similarly, if you consider that is what we have written here, Ax equal to x1 a1 plus etc xn an. So that will give the relation rank of t is same as column rank of A. Now we can consider the row rank. That is because of this equation Ax equal to 0. When you consider the null space of t here, then that can be written as nullity is same as nullity of t is same as dimension of the solution space of Ax equal to 0. Okay, the solution space of this Ax is denoted as S, then that is same as dimension of S. So nullity t is same as dimension of S. Okay, now we evaluate what is dimension of S. We have already discussed in the example 15 that dimension of S is same as n minus row rank of A. So that is equal to n minus row rank of A. I'll write here row rank of A. So then use rank and nullity theorem. Rank t plus nullity t is equal to the dimension of V. Okay, what is dimension of V here? What is V here? We are considering this t from a linear transformation from this is the definition of t from n dimensional vector space to m dimensional vector space. Okay, if we consider this is our V and this is our V and this is our W, we can say that this t is a linear transformation from V to W. Then dimension of V is same as n. So we can replace this right side by dimension of V. Consequently, that is equal to n. Then what is rank of t? Rank of t is equal to column rank of A. And what is nullity t? Nullity t is equal to n minus row rank of A, which is equal to by rank nullity theorem equal to n. You can cancel these two n. Then consequently, you can get column rank of A equal to row rank of A. Okay, so for any matrix, the column rank coincided with the corresponding row rank. Okay, with this we can conclude this first session.